Hello and welcome to Morehouse's Math Menagerie. Today we're going to be talking about correlation. You will recall that we discussed linear correlation previously in the course. In Chapter 10, we're going to discuss running significance tests on correlation and linear regression, and also talk about some other modeling techniques. Linear correlation measures the direction and strength of a linear relationship between two quantities or variables. We called correlation R previously, but R was really the sample correlation since we were always dealing with sample data. If we ended up with population data, then the population correlation would be rho. It kind of looks like a P, but it's a Greek letter rho. The correlation coefficient is on an interval between -1 and +1. The further it is away from zero, the stronger the linear relationship is between the two variables. So a correlation coefficient of 0 would be no association, where a correlation coefficient of 0.7 would be very strong association. And here's a few reminders about how correlation works. R is calculated using standardized values of both variables. Remember that standardized values are unitless. So since R is calculated from unitless values, it also is immune to the effects of units. So if you convert between inches and feet or feet and meters, the R value will stay the same. Correlation only describes linear relationships, not curved relationships. We are going to discuss later in Chapter 10 how we handle curved relationships, but correlation coefficient R is only describing linear relationships. The correlation coefficient is not resistant to extreme values. If we end up with an outlier, it's going to have a very strong effect on R. And correlation is not a complete summary of two variable data. As we'll see in a few minutes, sometimes even if we get a strong R value, we actually don't even have a linear relationship. When we run a significance test for the R value, the hypotheses are that rho equals 0 or there's no association, and the alternative hypothesis is that rho does not equal 0, which indicates that there is an association. What they're going to do for part of this section is they're going to give you this list of values in a table. You can see here we have n, which is the sample size. We have a column that's for a significance level of 5%, and then another column for the significance levels of 1%. Both of these two columns contain critical values that we will compare to R. If the absolute value of our correlation coefficient is greater than the critical value given in the table, then we're going to reject the null hypothesis. If it is less than it, we're going to fail to reject. Now, we're going to talk more in 10.2 about least squares regression, but you'll recall that we have a linear model that we built to help describe these linear relationships. Y hat equals B naught plus B1 times X. Here, the B naught is the y-intercept, and the B sub 1 is the slope. For the population, beta sub 0 is the y-intercept if we had population data, and beta sub 1 is the population slope if we had population data. So this model we discussed before was again based on samples. So B sub 0 and B sub 1 are sample statistics. Beta sub 0 and beta sub 1 are the parameters for the entire population. The reason we're discussing this is because we need to talk about how the correlation coefficient for data compares to the slope of the model. It turns out that if you take the correlation coefficient for a set of data and you scale it using the sample standard deviations, that equals the slope of our regression line. So when we run hypothesis tests on the correlation coefficient, when we're saying rho equals 0 or rho does not equal 0, that is equivalent to saying the slope equals 0 or the slope does not equal 0. These are equivalent statements. As we run the test on rho, we're going to see that a lot of the times in StatCrunch, they're actually discussing it in terms of the slope. But since these are equivalent, we can use those numbers anyway. Now, before we jump into a few examples, I wanted to show you this really cool relief map of Idaho I saw online recently. I want to run through quite a few examples with you today out of the homework, just because the concepts we talked about and then how StatCrunch presents them is quite different often. And I want to make sure you feel comfortable with doing the problems in the homework and on the quiz. So let's start with number 2. 54 wild bears are anesthetized, and then their weights and chest sizes are measured and listed in a data set. Results are shown in the accompanying display. Is there sufficient evidence to support the claim that there is a linear correlation between the weights of bears and their chest sizes? When measuring an anesthetized bear, it is easier to measure chest size than weight. If so, does it appear that a measured chest size can be used to predict the weight? Use a significance level of alpha equals 0.05. So the first thing we're going to do here is we're going to say for the null hypothesis that rho equals 0, and for the alternative, rho does not equal 0. Let's check those. All right. Identify the correlation coefficient. Well, we have this output over here that tells us all the good stuff. So here R is 0.976. It wants 3 decimal places, so 0.97. Oh, I better go 77 if I round it correctly. Next, it asks us to identify the critical values. Well, instead of giving us a table here, they just gave it to us in this output. So it says the critical R is plus or minus this 0.268 and some change. So we're going to say, hey, there are 2, because we have a plus or minus, and we're going to type this in here, 0.268 should be enough, enter. All right, it likes that. And it says, is there sufficient evidence to support the claim that there is a linear correlation between the weights of bears and their chest sizes? Choose the correct answer below. If necessary, fill in the answer box with your choice. Our correlation coefficient was 0.977. That is larger than our critical value, so we are going to reject the null hypothesis that there is no correlation in favor of the alternative that there is a correlation between these two variables. So we're going to say yes, because the test statistic falls between the critical values, or yes, because the absolute value of the test statistic exceeds the critical values. We're going to go with D here and say the test statistic, which is our correlation coefficient, 0.976, it wanted 977, exceeds the critical values. All right. When measuring an anesthetized bear, is it easier to measure chest size than weight? If so, does it appear that a measured chest size can be used to predict the weight? Well, they already told us it was easier to do chest size than weight, so the answer is going to be yes. Since it's easier, and we have a strong correlation here, so we can use chest size to predict weight. So let's read through these yeses. There's 3 of them. Yes, it is easier to measure a chest size than a weight because measuring weight would require lifting the bear onto the scale. The chest size could not be used to predict weight. Ooh, that's not good. We're going to toss that one out. Answer C says it is easier to measure a chest size than a weight because measuring weight would require lifting the bear onto the scale. The chest size could not be used to predict. Oh, we don't like that one. So the answer is going to be D here, but let's read through it just in case. Yes, it is easier to measure a chest size than a weight because measuring weight would require lifting the bear onto the scale. The chest size could be used to predict weight because there is a linear correlation between the two. Let's check our answer. All right, it likes it. Let's move on to the next question. Number 3 says a data set includes weights of garbage discarded in 1 week from 62 different households. The paired weights of paper and glass were used to obtain the results shown to the right. Is there sufficient evidence to support the claim that there is a linear correlation between weights of discarded paper and glass? Use a significance level of alpha equals 0.05. Let's look at our null and alternative. Our null is that rho equals 0. There is no correlation. and the alternative is that rho does not equal 0, that would indicate there is a linear association. Identify the test statistic R. Over here, they give us the variables for paper and glass. The correlation matrix is what they're calling this. So when you look at this, paper correlates with paper perfectly. Glass and paper interacting, that's going to be our R correlation coefficient, 0.4168. So let's type that in here, 0.417 if we round correctly. All right. And this is identify the critical values. Okay, our sample size is 62. So let's open up our table here. Scroll down. We have an alpha. What was the alpha? The alpha was 5%. So we're only going to look in this column here. We don't care too much about the 1% column because our alpha is 5% and our sample size is 62. So we're going to go to the lowest number on here. We're going to round down to 60. Even if it was 68 or 69 for our sample size, we would always round down. So for 60, it's 0.254. And there will be two of them. 0.254 because, it didn't type it in 0.24. Now, because we're doing a not equals to here as our alternative, there's going to be two critical values. That's why I said there are two. So let's check that answer. Oh, why did I open that back up? Let's check our answer. Awesome. Now we're going to compare the correlation coefficient to our critical value. The absolute value of this is 0.417. That's larger than 0.254. So we are going to reject the null hypothesis. Because the absolute value of the test statistic is greater than the positive critical value, there is sufficient evidence to support the claim that there is a linear correlation between the weights of discarded paper and glass for a significance level of 5%. Let's check our answer. Nice. Number 4 says, use the given data set to complete parts A through C, use an alpha of 5%. And we're given here the data. So instead of a summary table, we're given the data. And the first part says construct a scatter plot. So let's open this up in StatCrunch first. Once we have the data opened in StatCrunch, to make a scatter plot, we can go graph, scatter plot, and then select our X and Y variables. X and Y is really nice because the X variable is just X and the Y variable is just Y. There's a bunch of options here. We're going to kind of ignore that and just hit compute. And this is a picture of our data. We can see we have a little bit of a hooked shape here. So let's go and look at our graphs. It looks like B is going to be the correct answer here. Nice. Next, it says find the correlation coefficient. So back in StatCrunch, we're going to close out this graph. We're going to go stat regression simple linear. Again, select the X as the X variable, the Y as the Y variable. They have some stuff going on down here in terms of intercept and slope. We're going to ignore that for now. We don't need to run a hypothesis test here, but this will calculate the coefficient for us. Here we have the output. A bunch of stuff's going on here, so I'm going to go ahead and talk about this. It tells you that the model is y equals, here's our y-intercept, plus the slope times x. It tells us our sample size is 11. It tells us the correlation coefficient is 0.815 and some change. We have an r squared, and we have an estimated error standard deviation, and then a bunch of stuff down below we'll talk about later. For this question, we only care about the correlation coefficient. So we're going to say here for 3 decimal places, 0.815. 0.815. Answer? All right. Now it asks, using the linear correlation coefficient found in the previous step, determine whether there is sufficient evidence to support the claim that a linear correlation between the two variables. Choose the correct answer below. For this, we need to open up the table of critical values. Our sample size was 11 and our alpha is 5%. So I'm going to be in this middle column of 5% for our alpha, and I have a sample size of 11. So my critical value is 0.602. Our correlation coefficient is larger than 0.602. So we're going to say that there is sufficient evidence to suggest a linear relationship between these two variables. So let's read through our option. There is sufficient evidence to support the claim of a nonlinear correlation. There is sufficient evidence to support the claim of a linear correlation between two variables. B is going to be our answer because R measures linear relationships. So we have to say that evidence suggests there is a linear correlation. Even though the graph suggests otherwise, we were making this decision based on R. Let's check that answer. Now, last part. Identify the feature of the data that would be missed if part B was completed without looking at the scatter plot. Choose the correct answer below. The scatter plot reveals, or does not reveal, a distinct pattern. The scatter plot reveals a distinct pattern that is a straight line with negative slope. Well, that's not true. The scatter plot reveals a distinct pattern that is not a straight line pattern. The scatter plot reveals a distinct pattern that is a straight line. Well, looking back up at the scatter plot, we can see this is clearly a curved pattern. So the answer is going to be C. Even though we had a strong correlation coefficient that suggested a linear pattern, we still need to look at the graph and see if that makes sense. For this data, it obviously does not because of the curved pattern. These other three graphs are fairly linear, but this one has an obvious curve to it. Number 6 says, refer to the accompanying scatter plot. The 4 points in the lower left corner are measurements from women, and the 4 points in the upper right corner are from men. Complete parts A through E below. And we have this graph. I'm going to go ahead and pop it up. It's a little bit bigger. And we just have these clumps. It's kind of a bizarre scatter plot. We just have these two clumps, these two squares of data. Let's go back and read the problem now. Part A says, examine the pattern of the 4 points in the lower left corner from women only and subjectively determine whether there appears to be a correlation between X and Y for women. Choose the correct answer. So these data points down here are from women, and we want to determine if there's a linear pattern. I don't think there is much of a linear pattern because they're kind of a square. So we say there appears to be a linear correlation. No. There appears to be a linear correlation. No. There does not appear to be a linear correlation because the points form an obvious pattern. Part D, there does not appear to be a linear correlation because the points do not form a line. We're going to go with part D here. B, examine the pattern of 4 points in the upper right corner for men only and subjectively determine whether there appears to be a correlation between X and Y. Well, that pattern is the same as the pattern from the women, so the answer has to be the same. There does not appear to be a linear correlation because the points do not form a line. Right. Part C, find the linear correlation coefficient using only the 4 points in the lower left for women. So they don't give us the actual coordinates here, so we're going to open this up and we have to find the coordinates ourselves. So I'm going to open up my StatCrunch, close this out. I'm going to do it over here. There are 4 points on this graph. We'll call this the X and this the Y. The first point is at 2, 1. So I'll type in 2, tab over and put in a 1. The next person was at 2, 2. So I'm typing 2, 2. This lower right-hand dot is at 3, 1. And this upper right-hand is at 3, 2. Now I can go to Stat, Regression. Oop, I clicked on the wrong thing. Stat, Regression, Simple Linear. And I'm going to select the second X and the second Y. And I'm going to hit Compute. And again, it gives us all this information. But what we really wanted was the correlation coefficient, which was 0 here. So going back to our problem, we can type in 0. There is no correlation between these points. All right, like that. Next it said, do the 4 points in the upper right-hand corner have the same correlation coefficient? The answer here is going to be yes, because they have the exact same pattern as the 4 points in the lower left-hand corner. So the answer here is yes. Correlation does not care about where you're at on the graph in general. It only compares you to other points. It's relative to the rest of the data. So let's check that answer. Awesome. Part D, find the value of the linear correlation coefficient using all 8 points. What does the value suggest about the relationship between X and Y? Use an alpha of 5%. So let's go back to StatCrunch. Oh, actually, I need to open this up, make it bigger first. Move it over here to the side. StatCrunch. Now, we had the lower 4 points already put into this graph. So let's do the upper ones. It looks like the lower left-hand square is going to be at 8, 9. So we'll do here 8, 9. Upper left hand is going to be at 8, 10. The lower right hand looks to be at 9, 9. And the upper right looks to be at 9, 10. And now I'm just going to repeat that regression analysis on all 8 of these points, simple linear. The second X and the second Y. I'm going to hit compute. And we can see here it actually gives us a very strong correlation coefficient now. 0.9787. Let's go back here. 0.97, I think it was 87. So if we round it, it'll be 979. Let's check that answer. All right, it likes it. So using an alpha of 5%, what does this R suggest about the relationship between X and Y? Well, here it didn't give us the table. So let's go back to problem number 4. Yes, I want to leave this question. Or maybe 5. Oh, 5 has the table. So our sample size was 8, and we're using an alpha of 5%. So our critical value is 0.707. Going back to problem 6, our correlation coefficient was very, very high. This is larger than the critical value. So there is sufficient evidence that this is a linear relationship. So we need to look at just B and D here to find our answer. There is sufficient evidence to support the claim of a linear correlation because the correlation coefficient is greater than the critical value. Oh man, we hit money on the first answer. We can hit B here. Now, I want to emphasize here at this step that the last 2 examples have shown that having a high R value suggests a linear relationship. However, we have to look at the scatter plot to see if that makes sense. Remember in the slides, we mentioned that R is not a complete description of 2 variables relationships, and this is an example of why. Let's check that answer. Part E, based on the preceding results, what can be concluded? Should the data from women and the data from men be considered together, or do they appear to represent 2 different and distinct populations that should be analyzed separately? Well, these are obviously 2 groupings that are very different from each other. So despite the strong linear correlation that happened when we combined all 8 of them, they should not be. So we're going to say here, there are 2 different populations that should be considered separately. B, check that answer. Nice. Next problem. All right, number 7 is our last example, so let's get to it. Listed below are amounts of court income and salaries paid to the town justices. All amounts are in thousands of dollars. Construct a scatter plot. Find the value of the linear correlation coefficient R. Find the p-value using alpha equals 0.05. Is there sufficient evidence to conclude that there is a linear correlation between court incomes and justice salaries? Based on the results, does it appear that justices might profit by levying larger fines? For the null and alternative hypotheses, we're going to claim there's no association, and then we're going to investigate to see if there is an association. So we are going to select This, our null, is that the correlation is 0, and the alternative is that it is not 0. So let's select C there. All right, it likes that. Now it says construct a scatter plot. Well, we're going to have to get this data into StatCrunch eventually, so let's just go ahead and do it now. Once we have the data open in StatCrunch, we know from reading the question they're going to ask about the correlation coefficient and the p-value. So instead of just doing a scatter plot separately, what I'm going to do is go to Stat, Regression, Simple Linear. I'm going to select my X variable as court income and justice salaries as my Y variable. We already have the hypotheses set up here, but I'm going to scroll down, and I think there is a spot where I can ask it to do the scatter plot. I think if I select this right here, fitted line plot, it'll do it for us. Let's compute. Now we have our normal output from linear regression, but if we arrow over here, it has given us the scatter plot and also drawn the line of best fit. So let's go back to our options here. It looks like C matches the best. So I'm going to select C. Let's check that answer. All right. Now it asks for the correlation coefficient. So I'm going to bring back up my StatCrunch, go back to the output. Right here, it says R, the correlation coefficient is 0.8707. They want 3 decimal places, so 0.871. 0.871. Wonderful. The test statistic T. Now here, remember before we talked about in the slides that the slope and the correlation are related. If the slope is 0, then the correlation coefficient is going to be 0 as well. So we're going to look down here at this parameter estimate, and you can see there's a row here that talks about slope. It gives us the slope estimate, right? So you can see that's the same as what's in our equation up above. And it says our alternative hypothesis is that it does not equal 0. Well, when we ran this linear regression, what it did is it ran a test on the slope and got a t-test statistic of 4.684 and a p-value of 0.0023. Since running a test on the slope is equivalent to running a test on the correlation coefficient, we can use this test statistic and p-value to answer the question we have about our correlation coefficient. So here, to 3 decimal places, 4.684, 4.684, that was a 5, 4. All right, it liked it, and then it asks for a p-value. So going back to StatCrunch, we can say 0.0023, 0.0023. Oh, it didn't like it. Oh, I put in too many decimals. So it'd be, to 3 decimals, it'd be 0.002. I hate when it does that kind of stuff. Right, now it likes it. The last part says, because the p-value is less than 5%, there is sufficient evidence to support the claim that there is a linear relationship between court incomes and justice salaries for a significance level of 5%. Check that answer. Nice. Last part here. Based on the results, does it appear that justices might profit by levying larger fines? Let's read through our possible answers. It appears that justices profit the same despite the amount of the fines. It does appear that justices might profit by levying larger fines. It does appear that justices might profit by issuing smaller fines. It does not appear that justices might profit by levying larger fines. We had a strong correlation coefficient that is positive. A positive correlation coefficient says that as the X value gets larger, so does the Y value. So as court income increased, justices' salaries increased as well. We decided that there was a linear relationship going on here with our p-value by running the test. So we're going to say B, it does appear that justices might profit by levying larger fines. Check that answer. Great. Well, thank you for watching the video today. Remember to use that Ask My Instructor button if you have questions, and I'll email you back as soon as I can. Thank you for joining us. Have a great day.